Hello, everyone. My name is Varsha Naik. I'm a DevOps engineer working for an insurance company by name Tryg, and I'm here to share with you in this session our experiences with the container engine for Kubernetes and also the ways in which we optimize the resource utilization on our cluster. So let's get started. A little about our company. We are Scandinavia's largest non-life insurance company. We are headquartered in Valhalla, Denmark. We have over 5 million customers. We have over 7,000 employees. And talking about the market share, we hold the top three positions in spread across Denmark, Norway, and Sweden. And in Denmark, we hold the topmost position with the maximum market share. We provide for a large variety of insurance products and in various business sectors. Be it private, for example, we have health insurance, pet insurance, property insurance, and in various others. In commercial, we have small and medium sized business insurances, we have property insurance, and many others. And corporate, we have workers' insurance, liability insurance. As you can see, we have a wide spectrum of insurance products that we make available for our customers. So, what does this mean? We have a large amount of data flowing from various different sources coming to us at real time, and many of these sources are structured, few others are unstructured. And the density of each of these data from every source can be as huge as few terabytes. And what we want to do is we want to be able to structure them, model them in something called a COD model, which is a standard for insurance. We want to be able to centralize and streamline this data and then make it available for our STP, which is straight through processes, and our analytics and business intelligence services. This is just to make sure that the financial processing happens way faster without any manual intervention. Of course, like it sounds, it's a little technical, and there are various technologies involved here. And we have cloud native applications that are to be deployed on a Kubernetes cluster in the form of pods. And that's what we are going to do now. So the agenda for this session would be we'll discuss a little about the architectural overview of how we deploy things onto the Oracle Kubernetes cluster and the challenges that we face in the journey. We'll also discuss a few solutions to these challenges and various optimization techniques, starting with how do you select the node shape? That's also a part of optimization. And also, we venture into a few autoscaling techniques that we have incorporated in our cluster. And then we also would be very glad to share our optimization stats. This is picked up from our real-time production environment uh, during the time of presentation. And how much are we saving when it comes to the resources is what we would discuss there. And then we'll venture into the summary, a few key takeaways from this session. So coming to our deployment overview, how do we provision our Oracle Kubernetes cluster? We use Terraform, which is an infrastructure as a code. This is because it's reusable code and we can also collaborate with our engineers in the team. We have cloud native applications which are deployed in the form of pods onto the Kubernetes clusters. We use Helm charts for these, and the whole thing is deployed using GitLab CI/CD pipelines. To start with, we used a flexible VM shape as a worker node in the Kubernetes, and we use standard v4 flex to start with. When we did this, we had a lot of challenges facing us, one of which is we realized that our applications work differently. One group of application was CPU intensive, the other was memory intensive, few others were performance intensive. So we could not bring them all under the same umbrella and deploy them on the same underlying host. The next challenge was we started with the Kubernetes cluster on OKE, on Oracle, at a way early stage, and we had a huge or a large scale deployment. And every deployment of ours is having more than 2,150 pods. and that's the scale of the pods in every single cluster. Of course, we were sure to hit the edge cases here, and we did. And few of them I would want to surface here. One of it was we ran into this node not ready state issues, where the worker nodes used to constantly be unusable and they would go to the state called node not ready state. And this apparently happened because we had few applications which were so memory hungry that they used all the resources on the host, leaving the host itself no memory to perform. And we hence configured something called system reserved resources on the kubelet service on the host itself. And this can also be done using Terraform. So that's what we used. Also, we wanted to customize our worker nodes. So what we did was we used CloudInit to configure the max number of open files, and we also wanted to use Oracle OCI GrowFS to make sure we enhance the root volume and make it available, make the whole root block volume, boot volume available for use. So for all these customizations is something you can do using CloudInit scripts, and that's also possible from Terraform, and that's what we have done. The next challenge that we faced was a diversified workload. So, diversified meaning, as I discussed a little earlier, we had a lot of data, historical data, that had to be loaded. And for the first few days, all the applications would be very busy and the load had to complete and then come to the current view. Until then, all our applications were heavily used. And after that point, they were 70% of the times idle, and we were still having all static nodes and static number of resources configured, and hence we were paying the same amount during the busy hours and the idle hours. And the last challenge is like any other business would have, we had cost constraints, and we heavily had to bring down the cost consumption for every deployment in the production that we have. And I keep stressing on the point that we have a huge scale of deployment. So by that I mean for every single Kubernetes cluster in our production environment, we need approximately 500 vCPUs, 12 terabytes of memory, 300 terabytes of storage, and more than 2,000 pods. And this is just for one Kubernetes cluster. And at any given instance, we run about five of them. So the memory optimization was the need of the hour here. So talking about optimization of resources, we first started with node shape optimization. Oracle provides something called the flexible shapes of the VMs that can be configured as the worker nodes in the Kubernetes cluster. The user can configure the number of CPUs per the number of GBs of memory that a VM could have on a particular node pool. And this is configurable, and what we suggest is have node pools which are discrete. I mean, every node pool should be of a certain kind and should serve a particular or very specific purpose. So how about I deploy a very huge node with a large number of memory and CPUs assigned to it, just single node, and I force all my pods to be scheduled onto that node. There are few limitations here. We can have a limited number of volumes attached to a single node. So we might run into that issue, and hence we'll have to watch out. The other extreme where I say, okay, I'll have a very small node with very minimalistic amount of memory and CPU assigned to it. And as and when the number of pods increase, we would have more number of nodes, right? But then this again, if the number of nodes increase to an extent that you have exhausted all the IPs in your IP pool, then that again is a problem. So we have to make sure we choose the right shape of the VM and we have enough IPs to cater to all the worker nodes in the cluster. Also, we would like to suggest that not to have too many worker nodes or too many node pools in a cluster, just to ease our management of the cluster firstly, and also have discrete node pools with a specific purpose in every cluster. And further on node shape optimization, I would like to call this node type optimization. So our applications were of different kinds. Few were Java applications, which were AMD 64 based images. We also had something called Strimzy Kafka clusters, which are deployed as pods in our Kubernetes clusters. They were also AMD 64 based. So we conveniently deployed them onto standard v4 Flex VMs. We also had few Java applications which were ARM64 based images. So we could leverage the Ampere nodes here, which are way less expensive and very highly reliant and very highly performant. Also, we had a necessity that we wanted to deploy a database in the form of a pod. You would ask why? Because we wanted all our applications to be constantly talking to the database node, and if they are scheduled on the same cluster, then we would have the least amount of latency, and that's what we wanted to achieve. Also, Oracle provides something called the dense IO VMs, where there's a locally attached NVMe SSD disk, which of course because it is locally attached, it gives very low latency and it is having very high IOPS. So we could leverage this. So there are these three kinds or types of VM shapes that we used. And now we have become wiser with respect to the node selection and configuration of the nodes. But we could furthermore optimize the applications that are scheduled onto these nodes. And for that, we introduce autoscaling. So to start with, we have horizontal pod autoscaler. Let's presume that we have an application set or a controller, say stateful set or deployment, which has a certain number of replicas configured. And when there is peak traffic, we would want to have maximum number of pod replicas running at any given point in time. And when the load is basically idle, you would want to scale down the number of pods associated with the stateful set just to save resources. And how is this done? Using horizontal pod autoscaler. There are actually two ways of using the horizontal pod autoscaler. First way is you could monitor the pod's CPU and the memory, have a threshold configured in your horizontal pod autoscaler, and the pod autoscaler will tell your stateful set to scale up or scale down the pods correspondingly. Now, how do we do this? We have to install metrics server, which is an add-on. This exposes our kubelet metrics onto our Kubernetes API server, and that is made available to all our autoscaler tools in Kubernetes. The second way, which is the way we are using, is using custom metrics. So what we do here is we expose few application-specific metrics uh, to our Prometheus server running on the same cluster, and the Prometheus server, with the help of the adapter, makes it available to the Kubernetes API server, and hence it is fed as an input to horizontal pod autoscaler. Here again, we can set a threshold based on the custom metrics, and then you can scale up and scale down based on that particular metrics. So with this in place, we get to this graph. I'll tell a little bit about this graph. There is a tool that we have, a custom tool, which will monitor the number of pods, number of nodes in a cluster, the CPU and the memory utilization, and few other stats are collected from our production environment, which is our OK clusters in the production environment. And they are visible in the form of graph. And this is what we see here. The y-axis here represents the number of pods, and the x-axis is over time. Here you can see that the number of pods in our production environment has gone down to below 350 and has gone up to above 400 in a span of, say, half day or maybe one complete day. But are we saving anything as yet with horizontal pod autoscaler? The answer, sadly, to this is no, because we have only varied the number of pods that we are using in our cluster. But the nodes on which they are scheduled are still static, which would mean though we have reduced the utilization of the node itself is something we pay for, that's still the same. So to dynamically scale the nodes, we introduce cluster autoscaler. So what's a cluster autoscaler? In a Kubernetes cluster, let's presume there's a node 1, node 2, and there are 6 pods, and each of the nodes can cater to 3 of such pods. Let's now presume that there are 2 new pods that are coming into the cluster, And the cluster autoscaler then senses this and provisions a new node, and then schedules these two nodes onto the new node. This is how the scale up is done in cluster autoscaler. Now, scaling down, let's consider now that there are two nodes, node 2 and node 3, which have just one pod but are capable of hosting three pods of the same size. In that case, again, the cluster autoscaler senses this, it moves one of the pod to the node 2 and then decommissions or marks this node for decommissioning and hence scales down the number of nodes. So, is it available out of the box in Kubernetes cluster? No. We would have to add this together with the cluster. But this also gives us the opportunity or the liberty to play around with the configurational parameters in the cluster autoscaler itself. So, for example, if I have a cluster where there are three node pools and I want to be able to configure the number of dynamically scale the number of nodes in only two of them, I can very well do so using these parameters, say node and the node pool ID you provide, and that's what it'll do. You can also actually vary or decide how fast you want to scale down and using parameters like the scale down delay after add, and there are many such parameters you can play around with to suit your needs. So with cluster autoscaler and horizontal pod autoscaler, we get to see the node count over time. So you can see that initially when the node was high, the number of nodes had gone up to 100, and then gradually as and when the load decreased, the number of node counts also decreased. This is on one particular node pool the stats is collected on, which we would otherwise see a single straight line, horizontal line parallel to the x-axis. So are we saving money here after this horizontal pod autoscaler together with cluster autoscaler? Yes, we are, because we are varying the number of nodes, which would mean we are reducing the number of CPUs and the memories that we are consuming, and hence we save money. But is this enough? Our graphs say otherwise. So this is a graph collected by the same tool, but this is for the CPU and the memory consumption. And the red line here indicates the actual utilization of the resources, while the blue line indicates the pod requests. By request here, I would like to highlight, I mean the spec resource request, which is the guaranteed amount of resource the Kubernetes assigns a particular pod. So this is what we are actually paying for, and it's also a deciding factor for the cluster autoscaler that we saw previously. So we have a huge gap between the actual utilization and the requested resource. Why did we encounter this in the first place would be your question. And the answer to this is if I am a developer, I can make an educational guess as to how much resource my application would use when there's heavy traffic. And beyond that, I would keep a buffer and then configure my pod accordingly. And when there are too many pods, like 2000 odd pods configured this way, and this is what happens, then our guessing work will just cost us way too much. So we wanted something concrete to rely on, that we can configure our requests based on the actual utilization. And for this, we introduced a vertical pod autoscaler. I just want to highlight the fact that if you're using horizontal pod autoscaler with CPU and memory as the parameter, then you cannot use the vertical pod autoscaler. If you're using custom metrics in horizontal pod autoscaler, then you can use a vertical pod autoscaler to scale based on the CPU and memory. And what is a vertical pod autoscaler? In horizontal pod autoscaler, we increased or decreased dynamically the number of pods or number of replicas of a pod in a stateful set or deployment. Here, we change the size of the pod itself based on the utilization of the pod. We set a certain minimum and maximum values between which the vertical pod autoscaler tries to measure how much the pod is utilizing at any given instant, evict the pod, and restart the pod with the new parameters. Requested CPU and memory would increase, and you can configure at what interval it would evict, and all configure
in the configurational parameters. And this is how the scale up and scale down is done in the vertical pod autoscaler. You have, of course, this is also not available out of the box. You will have to configure it. And there are a few configurational parameters you can play around with for this as well. I've tried to highlight a few of the parameters here because we would want to let you know that this is something that you can do. We wanted to not be very aggressive with eviction of the pods. So we have set this eviction rate and rate burst and rate limit, the number of minimum replicas that has to be running at any given point in time for a stateful set or a deployment. And we could also configure as to which namespace should you confine your vertical pod autoscaler to. And many such parameters are available, so you can play around with this. And there's a little bit of experimentation it would take for you to get to the right value for your use case. But yes, it is worth it because you get to this. And this graph is basically another representation of CPU and memory again. And the red line indicates the actual utilization, and the blue line indicates the pod resource request. You can see that they are getting as close to each other as possible, but initially there's a spike. And this is what we have intentionally configured the VPA to do. And this is because we knew in advance that we would have heavy load in the beginning and we didn't want any kind of delay, and hence we have configured VPA in such a way. But this is what you would achieve at the end of cluster autoscaler, horizontal pod autoscaler, and vertical pod autoscaler. Now, together with all these optimization techniques, how much do we save, you say? Around 50%, to say the least. And these two tables, you might see slight differences in these two tables because we changed the shapes of or sizes of few of the nodes over time, but then the workload that it supports remained the same. So here you can see that the number of CPUs that we needed earlier were 4K, as opposed to now it is 1.7K. And even the memory is almost halved from 12K to 6K. And this is huge saving for us. And when it scales over 5 different clusters, it will be even more. And a few key takeaways from this session. We just need to be a little more aware of our application load type while choosing what kind of nodes and what are the shapes, and make an educative guess as to which shape would be needed and what processors can I use, and implement those node optimization techniques to the best of our ability. And then cluster autoscaler is something you configure on a particular node pool to scale dynamically the number of nodes in the node pool. Horizontal pod autoscaler is one level down, where you configure the number of pods that can be scaled up or scaled down at any given instant. Vertical pod autoscaler goes one level further down, where it ensures the request that we are doing to Kubernetes is as close to the pod's actual utilization as possible. Hope this session was of great value to you, and you will be able to utilize whatever points I made here. Thank you for your patient listening. Good day.